welcome to lecture series on advanced linear algebra. We have seen in our last lecture, if V is having direct sum decomposition by its subspaces W1, W2, Wk, then we have seen there exist k linear operators E1, E2, Ek, which are basically projection operators, such that the Ei square equal to Ei and Ei into Ej equal to 0 operators for when I not equal to j, and the identity operator can be written as a sum of operators E1, E2, Ek, and the range of each Ei is Wi, that is subspace Wi. And conversely, if we have k linear operators E1, E2, Ek which satisfies condition 1 to 4, then the vector space V having direct sum decompositions by the subspaces W1, W2, Wk, where Wi is the basically range of Ei. Now, along this space, suppose you want to add the typical characteristics of W1, suppose W1 is invariant under some linear operator T defined on this space V. I mean, if the W1, W2, Wk are invariant subspaces of V under the linear operator T defined on V. And if the space has direct sum decompositions, then also I will have this k linear operators E1, E2, E3 satisfying all these 4 conditions. But apart from this, we will also have some extra things. Let T be a linear operator on vector space V defined over a field, say capital F, and it is given to us, say V is equal to direct sum of W1, Wk, where each Wi is invariant under T. That is, this implies that T of Wi is subset of Wi. So, then we have already seen in our last lecture that one can introduce operators like T1, T2, Tk as a restriction of T on W1, W2, Wk. And then if I write here alpha, which is equal to having alpha 1 plus alpha 2 plus alpha k, since V is having direct sum decompositions. So, I can have this type of k tuple alpha 1, alpha 2, alpha k, where alpha will come from Wi and alpha can be written like this. This is coming as a consequence of the criteria already stated in above theorem, please. So, I equal to E1 plus E2 plus Ek. So, from that also I can have it. Okay. So, where alpha I belongs to your Wi. Then we have T of alpha is equal to T of alpha 1 plus T of alpha 2 plus T of alpha k. Even T is restricted to Wi, I have written this is the new operators called T1 alpha 1 plus T2 alpha 2 plus Tk alpha k. I have given the name like this. See, this Ti is operator on Wi on the subspace Wi please. So, in this situation we have seen if B1, B2, Bk are order basis of W1, W2, Wk, then B equal to B1, B2 and Bk is an order basis of V, and the matrix representation of T with respect to order basis B will of the form of something like A1, A2, AK, where AI is a square matrix of di cross di order, which is basically AI is the matrix representation of Ti on Wi, and sigma of di I equal to 1 to k is the dimension of the vector space V. So, we have seen like this. Now, question is under what condition is W1, W2, Wk will be T invariant. Now, question is under what condition each Wi will be T invariant. This one. Now, to answer this question, I will basically since most of the places in this course I will consider projection operator. So, instead of T1, T2, Tk, I will consider E1, E2, Ek type. Okay. So, to answer these questions, I am basically considering this problem please. So, this problem is basically some sort of I am writing theorem. Let V equal to W1 plus Wk, I mean V is the direct sums of W1, W2, Wk, and T is a linear operator, T be a linear operator on V. Since V is direct sums of W1, W2, Wk, so let K linear operators E1, E2, Ek which satisfied the condition Ei square equal to Ei, that is each Ei is a projection. Second, Ei into Ej equal to 0, the 0 operator for I not equal to j. Third, the identity operators is a sum of E1 plus E2 plus Ek, range of Ei is Wi. So, let V is direct sum of W1 to W2 k and T be linear operator on V, and E1, E2, Ek, there are k linear operators which are projection operators satisfying the criteria 1 to 4. Then each Wi is invariant under T if and only if T commutes with each Ei, that is TEI equal to EIT for I equal to 1 to k. So, if the operator T commutes with each of the projection operator EI, then the subspaces W1 to Wk will be invariant under T. So, let us give a quick proof to this problem. It is given T commutes with each EI. So, T of EI equal to EIT for I equal to 1 to k, it is given to us. Claim Wi is invariant under T. Let alpha belongs to Wi. Now, alpha belongs to Wi, this implies that alpha is the basically range space of EI. So, alpha equal to EI alpha. If I say that alpha belongs to Wi, then alpha equal to EI alpha. So, this implies T of alpha equal to T EI alpha. This is equal to T EI operating on alpha. So, this is I can write down EIT operating on alpha. Since EIT equal to T EI, it is given to us. So, I can write down T alpha is equal to EIT operating on alpha. So, this is equal to EI of T of alpha. So, certainly this will belongs to Wi. So, this implies Wi is invariant under T. Let us prove the other way, that is only if. This is first is if. So, now I am talking about the only if, this one basically only if, that is given each Wi is invariant under T. Claim that T commutes with each Ej, that is T of Ej equal to Ejt for j equal to 1 to k. I have to show that T of Ej equal to Ejt. According to given statement of the theorem, we have I equal to E1 plus E2 plus Ek. So, this implies that alpha operating on I equal to E1 alpha plus E2 alpha plus Ek alpha please. So, I have alpha equal to like this. So, this implies T alpha will be equal to sigma T Ei alpha, I equal to 1 to, okay. I mean to say T alpha is equal to T E1 alpha plus T E2 alpha plus T E k alpha. We have T E j alpha belongs to W j. Since E j alpha belongs to W j and W j is invariant under T. So, this implies each T E j alpha, for each T j alpha there will be beta j in W j such that this will be equal to E j beta j for some beta j belongs to W j. We have alpha is equal to E1 alpha plus E2 alpha plus Ek alpha. Now, T alpha will be equal to T E1 alpha plus T E2 alpha plus T Ek alpha, which I can write down sigma T Ei alpha. And when operating Ej from the left side, so I have Ej T alpha. Ej T alpha will be equal to how much? It will be again sigma Ej T Ei alpha, I equal to 1 to k. So, note that T Ei alpha will be in the Wi. So, according to our 1, so this is basically equal to sigma I equal to 1 to k Ej and Ei beta I from 1. So, this implies that Ej T alpha will be equal to Ej beta j. So, 1 and 2 implies that Ej T alpha equal to T Ej alpha. So, this implies Ej T equal to T Ej. So, T commutes with each Ej. So, T commutes with each Ej. So, we have seen the criteria of under what condition each subspecies Wj will be invariant under T. Now, let us apply this concept to a very specific problems when the operator T is having diagonalization structures. I mean when T is diagonalizable, let me see what this theorem says. Whether is it possible to have a simplified structure about this projection operator Ej or not. So, consider T as a diagonalizable operator on a finite dimensional vector space capital V. See, I mean in these theorems here I have not assumed that whether the vector space has to be finite dimensional or not. So, this results what we have considered is valid for finite or infinite both the cases please. Now, I am applying this concept when T is a diagonalizable operator defined over a finite dimensional vector space V. Let C1, C2, Ck be its distinct eigenvalues and W1, W2, Wk be the corresponding eigenspaces. Since T is diagonalizable, so eigenvector will form a basis for this space, and so certainly I will have V will have a direct sum decompositions of by its eigenspaces. So, V will have direct sum of W1, W2 and Wk. Okay. So, I will have V equal to like this. So, since V is a direct sum decomposition of W1, W2, Wk, our previous result says that there will be K projection operator, say E1, E2, Ek, where range of Ei is Wi. So, that concept will be there. So, there exist K linear operators E1, E2 and Ek such that Ei square equal to Ei, Eij equal to 0. Third, identity operator will be must be equal to E1 plus E2 plus Ek. Range of Ei is Wi. Now, the concept that T is diagonalizable, let us see what way this is helping us. So, we have for any alpha belongs to V, there will be K tuple, so that alpha is equal to alpha 1 plus alpha 2 plus alpha k, where alpha I belongs to Wi. I mean to say alpha 1, alpha 2, alpha k are the basically eigenvectors associated to eigenvalue C1, C2, Ck. So, this implies, and of course, we have T of alpha will be equal to how much? T of alpha 1 plus T of alpha 2 plus T of alpha k. This is equal to C1 alpha 1 plus C2 alpha 2 plus Ck alpha k. And of course, we have seen identity operator is equal to here E1 plus E2 plus Ek. So, then this means that alpha is equal to also we can write down E1 alpha plus E1 alpha will be basically C1 E1 alpha. So, this implies that I see that T is having of the structure of C1 E1 plus C2 E2 plus Ck Ek. So, when T is diagonalizable, then also I am getting there T of alpha, when alpha is equal to E1 alpha plus E2 alpha plus Ek alpha. So, T of alpha will be T of E1 alpha plus T of E2 alpha plus T of Ek alpha, but T of E1 alpha is equal to C1 E1 alpha, because E1 alpha is a eigenvector associated to the eigenvalue C1. So, similarly, I will have T equal to C1 E1 plus C2 E2 plus Ck Ek. Okay. So, this is the new feature I am getting, that the operator T can be written as C1 E1 plus C2 E2 plus Ck Ek, please. Previously, when it is T is not diagonalizable, suppose this diagonalizable is not there, so I can only write down the identity operator as the sum of projection operator E1 to Ek. But when T is diagonalizables, I mean when this in that case your eigenspaces are also invariant, then I am getting what? I am getting the operator T as a sum of C1 E1 plus C2 E2 plus Ck Ek. Now, this information will certainly help to talk about the structure of the projection operator as a function of T, because projection operator E, E1, E2, Ek, they all belongs to your LVV. So, certainly E1, E2, Ek one will be able to express as a linear combination of T to the power 0, T to the power 1, T to the power 2 and so on. I mean basis of the LVV, but for this diagonalizable operator case we can show that this projection operator is having typical simple structures. What is that? That I am showing it here. Suppose this is T is diagonalizable, then I see that T is of these structures. So, this implies T square will be equal to how much? It will be C1 E1 plus C2 E2 plus Ck Ek, this into C1 E1 plus Ck Ek. So, using the property that Ei into Ej equal to 0, this will give you C1 square E1 plus C2 square E2 plus Ck square Ek, because Ei square equal to Ei. So, based on that principle, I can write down the operator T square equal to C1 square E1 plus C2 square E2 plus Ck square Ek. So, in general T to the power r will be C1 power r E1 plus Ck power r and Ek. Okay. So, this implies that for any polynomial g x over the field f on which the vector space is defined, Gt will be equal to Gc1 E1 plus Gc2 E2 plus Gck Ek. So, the operator Gt which is defined over the vector space V, I see that having typical structure which is equal to Gc1 E1 plus Gc2 E2 plus like this. So, in particular when the polynomial Gx equal to having Lagrangian interpolation polynomial, say Px which is equal to Pjx is equal to x minus Ci I not equal to j divided by Cj minus Ci. I mean x minus C1 into x minus C2, x minus Ck excluding the x minus Cj, and the denominator it will be Cj minus, this is I please, Cj minus C1, Cj minus C2 and Cj minus Ck. If I consider like this, then we have Pj Ci equal to delta Ij, Kronecker delta, Kronecker delta function. So, this is equal to 1 for I equal to j, 0 I not equal to j. So, if I consider this type of polynomial function, then we have Pj t will be equal to Pj C1 E1 plus Pj C j minus 1 plus and Ej minus 1 plus Pj Cj Ej plus Pj Ck Ek, but all will be 0, x will have only simply Pj Cj Ej which is equal to Ej. So, this implies the projection operator Ej for this case is basically Lagrangian interpolation, operator Pjt, where Pj is a Lagrange interpolant polynomial function please. So, this is the beauty of this result please. So, we see that when T is diagonalizable, the projection operator having structure of the form Pjt, and that Pj is a basically Lagrange interpolant polynomial please. We will continue with the applications of these invariant direct sums and more, specifically for first I will talk about the diagonal operators, because I have assumed here that if T is a diagonalizable and V is having direct sum decompositions, then the operator T having a typical structure like C1 E1 plus T C2 E2 plus Ck Ek. But if suppose the T is operator defined over the vector space V, and V is also having direct sum decomposition of suppose W1 W2 Wk, where C1 C2 Ck are k distinct constant, then whether the operator T will be diagonalizable or not, that has to be proved please. So, this thing I will prove in my next class please.